So it says, not waffles. Very clearly says, not waffles on Wednesday the 23rd. Very clearly. Right here, very clearly says, not waffles on the 23rd. Please spread the word that there's definitely not waffles.
It's called Belgian Wednesday.
Exactly. All right.
What's the not Belgian waffles?
So, we use every time. So, yeah, being able to apply a graph like this. On a graph like this, questions that relate to this kind of stuff, I will always give you the graph. You don't have to try to memorize anything. You just have to be able to interpret a graph. So don't think like, oh my God, do I need to know all these? No, you need to just be able to read a graph and figure out what it is. You do have to do some basic things like identify the correct chemical, like potassium chloride. You need to know that there's a line that you have to find, and it's a little bit of a scavenger hunt. Now potassium chlorate, potassium chloride. So there's definitely a little bit of that kind of naming and formula stuff that you got to get. And again, you're going to try to find where the temperature and solubility kind of lines sort of cross. And then this particular bit at 30 degrees C, about 35-ish, 37-ish, whatever you want to call it, between 35 and 40 grams of potassium chloride will dissolve. If you dissolve exactly that much, it's a perfectly saturated solution. No more can dissolve, but no extras left over either. So if we try to put 50 in here, what's going to happen? I'm trying to put this much in here.
I have like 14 grams left over.
Yeah. I'm trying to put too much in there. So my solution, is it saturated or unsaturated? The solution that solves, that forms.
Saturated.
It'll be saturated with extra stuff settled out at the bottom. And how much extra? That much extra, about 15 G extra.
Yeah.
About.
That's cool.
Okay, trick question.
Uh-oh.
Now what's going to happen? I doubled the amount of water.
It's double 35.
So this actually, you can't read this directly off the map, off the graph here. You have to do a little bit extra with it.
Is it 70?
Okay, this graph, remember, this side here is still always out of 100 grams. So if I make it 200 grams, dump a bunch more water in there. Will it still be saturated or unsaturated at this point?
Unsaturated.
Okay.
Unsaturated.
So it's still about, let's call it 35-ish, right?
Mm-hmm.
35-ish grams at 100 grams of water. 200 grams of water, how much will dissolve? 70-ish. So now, if I put 50 grams in there in 200 grams of water, is it saturated or unsaturated?
Unsaturated.
Unsaturated. Because now it can hold about 70-ish, and it's only got 50-ish. So it'd be unsaturated with room for about 20 more grams or so. Make sense?
Yep.
Add more water, the excess stuff would literally just disappear.
You can only do that with the
What was that?
You can only do that with the line.
Yeah. The line ones. Or you can do it with the curved ones too. That's fine. Not these ones, but the ones that are going up. Sure.
Oh, yeah.
Still the same thing over. Any questions on this? Concepts of saturated and unsaturated. Okay, now here's the hard question. This is the one you're going to have to think about for a second. Give me an example of one compound from here. Yeah, one of these. This is going to be the hard part. Give me an example of one compound from here that if I made 100 grams of solution, so just using the regular side on here, that if I made it saturated, it would also be concentrated. Find me one compound that if I make a saturated solution, it will also be concentrated. Look at about 30 degrees because that's about our room temperature. It's a really good way to go. So what does the term saturated mean?
Means it's full.
Means it's full, holding as much as it can.
Mm-hmm.
What does concentrated mean? They're similar but different.
More than average amount of solutes.
Yeah, a relatively high amount of solute. Yes, I would agree with what you're saying there. Relatively large amounts of solute. So if we're looking at, say, 30 degrees, roughly room temperature, it's a little warmer than we are. Which of these compounds would be at saturation, also concentrated, lots of solute?
The red line.
Yeah, the red line would be a really good example of one that would be like that. At 30 degrees, if I put this much in here, if I make a saturated solution of sodium nitrate, it's also really concentrated. There's 90 plus grams of sodium nitrate in 100 grams of water. It's very concentrated when it's saturated. Opposite side, give me an example of a compound that is dilute when it's saturated. Same temperature.
Yep.
So same temperature. Find one that's dilute when it's saturated. Yeah, there's a really good example one. SO2, potassium chlorate. These guys, when they're saturated, they can only hold a very small amount of stuff that's in there. So even though they're saturated, they're dilute. They don't have a lot of solute. So those two terms don't mean the same thing. Saturated depends on what it is. Concentration just means like how much stuff is in there. So like paper, a piece of notebook paper will be saturated with water relatively quickly compared to an equivalent mass of, say, sponge. And definitely would be a lot more saturated than an equivalent mass of the stuff that they put in diapers. Sodium polyacrylate. There's that stuff that they put in diapers that absorbs so much water, right? And it turns into this gel. Hopefully you haven't seen diapers lately, but just in case. You maybe have little brothers and sisters. Or really, really old grandparents. Ooh. Oh, sorry. Too early. Too early. Okay, so saturated and concentrated are not the same thing. A lot of students mistake that. They think that they mean the same. And a lot of times they kind of similar, but definitely not. Saturated for certain things can be very dilute. Okay, Matt, moving on. So we're talking about concentration. Just fast forwarding past this activity because we didn't do it. It's fine. Come on. There, nope. Oh, yeah. So when we're talking about concentration, rather than just doing it generically, it's really useful to come up with it quantitatively, a math way of talking about what concentration is. Rather than just generally concentrated, generally dilute, there's numbers that we can use to express exactly how concentrated or exactly how dilute they are. There's two ways. One of the ways is in standard 15D. The second way is in standard 15E. So we will flip the page in just a couple minutes. So far, so good? Okay, so we're going to start with the basic one. The basic one is not used very much in chemistry. So I want to mention that at all. So why do we quantify concentration? Why would that be important? Have you guys ever used hydrogen peroxide?
Yeah.
Right, the stuff at your house. 3%. Hello. Success? Plenty of leftovers, right? Awesome. Oh, that's good. The stuff that they do hydrogen peroxide like with your teeth, if you're trying to do that sort of stuff, like we're trying to do teeth whitening, if you go to the actual like dentist, way higher concentration than that. If you're trying to use peroxide to dye your hair, about 20% to 30%. So if like you use peroxide at a salon, it's about 30%, the stuff that they bleach hair with. It's not actually bleaching. They don't really use that particular chemical compound, which is a different name. They usually use peroxide to bleach hair. 30%. If you put 30% hydrogen peroxide on a cut, how's that going to feel?
Ooh.
Nightmare. No, thank you. Some people gargle with hydrogen peroxide. I don't know if any of you guys do that. It's an old thing. Like if you have a sore throat or you're trying to brush your teeth, it's a more natural way to whiten your teeth, stuff like that. Again, you try to gargle with 30% hydrogen peroxide. It's important to kind of know what your concentrations are that you have, because sometimes you want really dangerous things to be dilute. You don't want to hurt yourself with them. For example, the fluoride in your toothpaste. That's the concentration of fluorine in your toothpaste. Any higher than that, and it's actually considered to be poisonous. But they don't let little kids. That's why they make toddler toothpaste doesn't have fluorine in it, because it's actually really poisonous. If you eat fluoride, it actually can be very toxic to your system. That's why they always tell you to use just a real small amount of toothpaste. That's why they don't make toothpaste taste very good, because it's poisonous.
What about our tap water?
The concentrations are even less than this.
Oh.
Yeah, you're talking about.
Whoa.
Yeah, I mean, it's really, really low concentration. It's enough to be able to get the beneficial parts of it, where it helps protect your teeth, but not enough that it gets into the toxic side. So many compounds that we have, that we use in our daily life, are at low concentrations beneficial and helpful, and at high concentrations are dangerous, toxic, even deadly, depending on what we are, including things like water, oxygen. I mean, basic stuff in our everyday language. Tylenol, ibuprofen, aspirin. There's a reason why there's daily dosages on those things. And a lot of kids don't realize this, but they abuse, accidentally, ibuprofen. Advil, the little brown ones, right? Yeah, and athletes especially, what they're starting to find is that people that are consistently taking high dosages of ibuprofen are causing kidney damage, liver damage, the two parts of your body that actually filter out toxins from your system. And people just think that because it's sold over the counter, that it's not dangerous, and that's not correct. You increase the concentration of anything to a certain point, and it's going to get bad to you. So we need to have ways of quantifying what concentration is. It's important to know, how dangerous is this stuff? Do I need to clear the room, or is it perfectly fine? Someone farts in the room, we do not need to evacuate. We fill the room with methane gas, high concentration, we need to leave, don't light a match, right? It depends on concentration. So the first way that we do this, really? The first way that we do this, and I call this consumer style, because this is when you go to the store, when you go to the grocery store, the pharmacy, whatever, your concentrations are going to be written like this. Consumer style concentration is called mass percent. That's the name of this process, because it's easy to understand. It's just not very useful chemically speaking. It's very generic in a chemical sense. It's a decent approximation, and it gives you a good idea of how much there is. But in terms of reactivity, it falls short. So mass percent is how we do this consumer style. So things like when we say vinegar, like you go get vinegar, it's 5%. When you get hydrogen peroxide, it's 3%. Isopropyl alcohol, 70%. That's what I'm talking about. These are called mass percents. So far, so good? You've seen these before, whether you know it or not. Simple formula, you do have to memorize this. You have to bring this formula to the test. I'm not giving it to you. So here it is. Mass percent is calculated as. Here's the formula. I'll get to this in a second. Mass percent is mass of solute divided by mass of solvent. Solution, sorry.
That was really simple.
It's super easy. Part over whole. How much stuff is dissolved in the whole quantity of stuff? There's two little tricks to how this gets rearranged. Okay, algebra fans, when you take a look at your standard, it says you have to be able to do problems on this, including algebraic rearrangements. Okay, here's what I mean by algebraic arrangements. Any one of these three things can be the x. In your notebook, you have to show all three versions, different problems that show this is the x, that's the easiest one, versus I'm solving for the mass of solute, versus I'm solving for the mass of solution. Those are the three versions I'm referring to. It's not supposed to be hard, but a lot of students don't know what I mean when I say algebraic rearrangement. So any one of those three things can be the missing piece. And not challenging other than the algebra part. So a couple of things that are a little bit tricky here. Notice how this says mass of solution. It is not the mass of the solvent. It's the mass of the solution, not just the mass of the solvent. It's the total mass, part over whole. But
with water?
With you, yeah, we're all pretty much always going to do water as our solvent. So, example, here's an example problem that you guys can copy this one. What's the mass percent of a solution created from 12.7 grams of sodium chloride and 50 mils of water? So this is an example problem. Take a second and copy that down. Show you how to do mass percent. This is a slightly harder version, not very, but slightly harder. So you should be okay on this one. Mass percent of a solution created from dissolving 12.7 grams of sodium chloride in 50 mils of water. Here's a couple of things that you need to know about this. So I'll give you a second to write that down. And then a couple of notes, a couple of things to annotate in this problem. That's what I'm solving for, mass percent. So I'm going to use this equation. Where's the mass of solute located in the problem?
12.7.
It's the 50 mils. Wait, is it solute or something?
Yeah, right. That's the word. That's the word part that gets tricky in here. Okay, mass of solute. Okay, solute, is that the salt or is that the water?
Salt.
Is it the salt? I think it's salt.
Salt. 12.7 grams.
Salt is the solute.
Okay.
Water is the solvent. So yeah, language-wise, that's what trips students up more than anything else. The math part, the plugging in the numbers and calculating is not hard. It's the decoding is always hard. So mass of the solute, this is usually going to be a salt of some sort. It isn't always, but that's a good kind of generic way to think about it. So in here, I actually use table salt. So this right here, 12.7 grams of sodium chloride. What is that?
Solute.
Mass of solute. This is the be careful part. 50 mils of H2O. Solute, solvent, or solution?
Solution.
Read it carefully. 50 mils of water. Is that solute, solvent, or solution?
Solvent.
It's a solvent.
Oh, the solution is both of them.
This is the caution part. This and this are not the same thing. What students want to do all the time is do 12.7 divided by 50 and just plug them in and go. And that's close. If it made 50 mils of solution, then you'd be fine. If this is 50 mils of water, so we're going to be a little bit careful of that. The other parts, just so you know, 50 mils is the same thing as saying 50 grams. Milliliters and grams are the same thing. 1 milliliter of water weighs 1 gram. So that's the other approximation that we're going to always use in here. Milliliters and grams mean the same thing. That's technically volume of solution, but we know that they weigh the same amount. So how do we figure out the mass of solution?
50 plus.
Ask Adam. So solution is solute plus solvent. Solution is solute plus solvent. So to do our final bit here when we do our mass percent, everyone abbreviate it is fine. There's no real official abbreviation for mass percent.
12.7 grams over.
It's solute over solution, which is 12.7 grams
Over 62.7.
over, I'm going to put it in parentheses just so other people know where it comes from, really. For people who knows where it, why?
I'm confused.
I am too. Where did it go? Undo delete page. Okay. I wonder where it went. There it is. So I deleted an entire page. Lovely. Okay. So my shirt. So 12.7 over 12.7 plus 50. I'm going to put a 50.0. Is it solute? It's solvent. I wonder what that, wow. So good. That's the mass of the solution. Solution is solute plus solvent. You have to have the two of them together. So then, because it's a mass percent, I forgot to put that in above. I always forget because I kind of assume that you know how to do that. Because it's a mass percent, you have to do the times 100. So basic calculation. 12.7 divided by 12.7 plus 50, which is at 67, is 0.20255 times 100, 20.255%. So it's about 20%. Take figs. I know we haven't. That's why I'm mentioning them again. Sig figs in our problem. How many do we have?
3.
3. Round it to 3. 20.2.
No, 0.3.
20.3%. That rounds up. So that would be our final mass percent in correct rounded sig figs. So again, not super challenging. It's just being able to identify which one's a solute, which one's a solvent, which one's a solution, and being careful about that part. You're going to have to find some problems that help you kind of figure that out, because the math itself is actually really easy. It's the decoding. It's the taking the time to read the problem, and I can't make you do that. You have to practice doing that and make sure that you identify the right part of the equation. Keep in mind that any of these problems, again, with algebraic equations, they maybe give you this one and say, what's the mass of salt, in a 40% solution? So you can go, all right, I have a 40% solution, maybe I have 100 grams of it. You can calculate for the other X. It's pretty straightforward, but again, you've got to be able to read, plug in the right numbers to the right parts of the equation. Okay, I'm going to move on. Okay, other part. Flip the page. So I'm trying to make sure I do this quick so I give you time to work. Yeah, exactly. Carbon mole's back. Okay, this is not the consumer method. This is the chemistry method. So this is the part you're not going to like as much. good. As far as I know, yes. Yes, please. Thank you. Bye. Okay. So the chemistry method, as opposed to just a generic percent by mass, we know that certain heavy compounds, like sugar, it can have a really high percent by mass, but yet the concentration is relatively low because each particle weighs a lot, so there aren't that many particles in there. And so in chemistry, it actually makes a lot more sense for them to discuss to figure out how many particles are present rather than just what the total mass is. Total mass is way easier just in terms of generically making one up. It's just less useful in a real specific chemistry kind of context. So in your daily life, mass percent is more important. If you ever take another chemistry class, chemists are completely obsessed by this concept. So this is the second method. Get this out of the way. So the second method, again, why is it important? Because this focuses on actual reactivity in actual chemical reactions, not just how heavy it is. And so this is called a different name. It's based after our friend called molarity, as in moles. Yeah, molarity as in moles is the name of this process, this way that we do chemistry, or this concentration. So mass percent is one style of consumer type of concentration. Molarity is the chemistry context for concentration as well. And with molarity, here's the equation for it. M, it's a big capital M. A lot of times it's either in italics or bold, so I kind of do a funky looking M thing like that. The big capital M, and it is not mass, it's moles. They're back.
Oh.
So it's moles, and just like the other one had solute on top, this one does as well. The other one had solution on the bottom, this one does as well too. It's not moles on the bottom, they actually do something on here that does make it functionally easier for us, but calculator-wise it's weird. It's quantity. Solutions are liquid, so they're like, how much is there? You don't usually weigh solutions. You usually get the volume of a solution. I don't tell you guys to go get me 250 grams of a solution. I tell you to go ahead and get me 250 milliliters of a solution. So that's what we're typically going to do. So the units for this, just so you know up there, what's the units of moles? MOLs. That's the units of moles. What's the units of volume? Milliliters or liters? Typically liters. So the units of molarity is moles per liter. Or you can just abbreviate with a big M. It's kind of nice. A lot of the solutions that we use in class, that we use consistently around here, about that. About 1/10 of a mole of reactant stuff per liter of solution. They're pretty dilute, so I don't kill all of you. Or me.
Okay.
Concentrated sulfuric acid. Scary. Sorry, that's hydrochloric acid. Concentrated sulfuric acid is that. That's as saturated as it can be. So there can be a really high range, but just to give you an idea of what ranges of these things can be. You know, we talked about things like, you know, nasty toxic stuff. You're usually talking like this in terms of really poisonous kind of stuff. I'm doing really nasty solutions. So they're fairly small numbers when we deal with these. So let's do a practice problem on this one. So you can figure out how this works. Not going to like it, but it's good review. Go ahead, take a second, write that down. What's the molarity of a solution created from 12.7 grams of sodium chloride, basically dissolved in enough water to make 750 milliliters of solution? There's our formula which we're going to need to use. Molarity is moles per liter. So that's our formula we're going to use. So what is the molarity of a solution created from 12.7 grams of sodium chloride dissolved in enough water to create 750 milliliters of solution? Okay, decoding the problem. What are we trying to figure out in this problem? We're trying to figure out this. Which symbol is that? M. We're trying to figure out the M. 12.7 grams of sodium chloride. Which of these other spots is that going to end up in, but not directly?
Liters.
This is not liters. That's going to end up in here, but it's not there yet. This is actually mass. It's not moles. How do we convert from grams to moles? No, we don't need Avogadro's number, actually.
You just need the.
We need the molar mass.
Okay.
No, we don't need Avogadro's number. I don't care how many particles are present. I just need the masses. Molar mass, nice review, comes from up there.
750.
So what do we got? It's sodium is 22.99.
28.48.
Chlorine is 35.45.
58.48.
58.44 grams. Okay, again, that was masses from the periodic table. I found the mass of sodium, I looked it up. Found the mass of chlorine, I looked it up. Added them together to get the molar mass of sodium chloride. Yeah, sorry, I told you it was going to be math. Divided by 58.44. Our final answer here is 0.21. I'm going to do 3 sig figs. You have 217 moles NaCl. Stop. There we go. So a lot of times you'll be given problems like this. Molarity is moles per liter. Many times you're going to be given mass. So you'll have to convert mass grams to moles first. It's just a little simple wonder fraction like that. It's just figuring out what the molar mass is. Okay, liters. Do we have liters?
Yeah.
We have milliliters. If you're not sure how to convert milliliters to liters, again, it's been a little while. You'll remember how to do it. By the way, 1,000 milliliters equals 1 liter.
Yeah.
So move the decimal place over 3 places. 750 milliliters equals 0.750 liters. Divide by 1,000. Okay, we have to use liters in here. You were given milliliters. So you just divide by 1,000. 1,000 milliliters equals a liter. Comes way back when. So again, move the decimal place over 3 places. Or hit your calculator, divide by 1,000. So when we do our final math, molarity is moles per liter. We're solving for molarity. Do we now have the moles to put in there? Yep, 0.217. Do we have liters to put on the bottom?
Mm-hmm.
Yep, we figured it out there. 0.750. And then it's just a simple division. 0.217 divided by 0.750 is 0.289. Move that up for you guys to see it. Units can be written in 2 ways. They are both correct. So you decide which units you want to use. You can either write this as 0.289 with the capital M next to it is totally fine. That's a great way to use the abbreviations a little bit faster. What?
I thought that was the volume of the entire solution, so don't you have to add mass to water?
Okay, good. Yeah, I'll come right back to that. You can write it either way. They're both okay. Either units is fine. They mean the same thing. So whichever units you want to use, just pick one that you like that looks better to you and use it. A lot of students end up using this, but the equation says moles per liter in it, so they want to use that. All right, so to answer Monty's question, I thought it was liters of solution.
Mm-hmm.
Look at the way the questions are worded. They're always worded in a real subtle way here to kind of help you with that. And it's worded to create 200 or 750 milliliters of solution, not water.
Oh, sweet.
And typically that's how they are worded to not trick you. Okay. All right, so there are 2 simple formulas. One's mass percent, it's consumer use. One's the molarity one. Molarity, if you have to pick one of the 2 for this chapter for your final, molarity is the one, because this is chemistry class, molarity is the one I'm going to focus on more. So 15E is more important overall than 15D is. There are some problems that use 15D as well, but 15E does more stuff. It also helps you review how to do molarity, molar mass, which we're going to use in dilution. We're going to use it in stoichiometry, the stuff when it comes up. So on both of these standards, it says you have to do the algebraic rearrangements. That means you can solve for any one of those three, either solve for molarity, solve for moles or grams, or solve for liters. Where do you get the problems to do this? Chemistry's full of problems, right? Yeah, so a couple of different options. And it kind of says it in there, but I want to remind you where you get these from. I did not specifically leave a list of problems. I need you to get to the point where you can kind of start to pick some problems to use for this. So problem sources that you can use. You can make one up. I mean, literally, just like I made up like this one on here. What's the molarity of a solution created from 75 grams of silver chloride in 300 milliliters of solution? You can just make up different numbers and plug them in. What? Yes. You will, no, yes and no. You will have solubility rules on the test. I will not give you your polyatomics. Actually, maybe I will give you those 4 or 5 polyatomics.
Wait.
I'd like 5.
Kobe just asked, will you have this on the test?
Mhm.
And I probably will give it. I'll give this to you on the test.
Firecrackers.
Yeah, yeah.
I'm not gonna give you more than 5.
Yeah, no, I'll give you those couple. So where do you get the problems from? Chapter textbook. Yay! There's textbooks back there. If you need to, come grab a picture. The questions are located at the back of chapter 15. The back of chapter 15. Your textbook is online. You can look at that too. Yay! I'll remind you where this is, by the way, online. It's on the classwork page at the very top. So get it, really. It's on the top of the classwork page whenever it wakes up. You can get it to it that way. You can have each other make up problems and do something similar like that. If you get stuck, come find me. You can Google practice molarity problems. Find some. However, I am going to ask that in your notebook, you write the problem out. Don't just show numbers. I want to know the problem that you're doing. If I start to see like 2 problems that everyone's doing, I'm going to wonder. But this is the math that comes on this chapter. It's pretty easy math. You just got to go find the problems that make sense for you. And again, I want you to make the decision making to find those problems, because as always, it's the wording that's hard. And so you got to get used to looking at different kinds of wording. Yeah? All right, I'm done with you. You got half an hour. You can be working on a notebook. You can be working on old tests. You can be working on finding the World of Chemistry book. You can check, do anything that you need to do. I'm giving you half an hour. This needs to be work time. So make sure that you're getting something done. Hey, look, there it is. They changed the look at Classroom, just so you know.
Whoa.
Yeah, they updated it. They changed the look at Classroom, which is why I wanted to show it to you. It's on the top of the Classroom page. It's right there.